Hello everyone. Today I will be presenting our research on SRGAN and the unreasonable effectiveness of deep features as a perceptual metric. This presentation covers the evolution of image super resolution techniques from traditional CNN approaches to modern perceptual evaluation methods. Our agenda today covers three main topics. First, we'll explore image super resolution fundamentals and examine SRCNN as the pioneering deep learning approach. Second, we'll dive into SRGAN's revolutionary use of adversarial training for realistic super resolution. Finally, we'll discuss LPIPS as a modern perceptual metric that better captures human visual perception. So, what is an image super resolution? It is the process of generating high-resolution images from low-resolution inputs. This technology has numerous practical applications including photo enhancement for consumer photography, medical imaging where detail preservation is critical, and low-bandwidth video streaming where efficient transmission is essential. Traditionally, this problem was solved using interpolation methods like bicubic upsampling. However, these approaches are limited in their ability to create fine details and textures. Deep learning has enabled us to move beyond these limitations by learning complex patterns from training data. For our experiments, we've utilized the diff2k dataset, which contains high-resolution images with at least one dimension exceeding 2000 pixels. This dataset provides diverse content across various domains, making it ideal for training robust super-resolution models. Now, let's talk about some SL models. SRCNN, introduced in 2015, marked the first successful application of deep learning to super resolution. Its approach is pretty simple. Take a low-resolution image, upsample it using bicubic interpolation, then refine it using a 3-layer CNN. The architecture consists of 3 distinct stages. First, feature extraction uses large 9 by 9 filters to capture spatial patterns. Second, nonlinear mapping transforms these features through 1 by 1 convolutions. Finally, reconstruction combines the mapped features to produce the high-resolution output using 5 by 5 filters. The training objective uses MSE loss, optimizing for pixel-wise accuracy. While this approach achieved state-of-the-art results at the time, it inherently tends to produce smooth, average results rather than sharp, realistic details. Now, let's move our main topic, SRGAN. SRGAN, published in 2017, revolutionized super resolution by introducing adversarial training. Instead of pre-upscaling inputs, SRGAN performs internal upsampling and focuses on perceptual quality rather than pixel-wise accuracy. SRGAN consists of 2 key components, the generator and the discriminator. The generator is responsible for creating high-resolution images from low-resolution inputs, while the discriminator tries to distinguish between real high-resolution images and those generated by the network. This adversarial setup helps the generator produce images that are not only sharp, but also visually realistic. SRGAN's training is guided by 2 main types of losses. First, the adversarial loss, implemented as binary cross-entropy loss, and second, the perceptual loss, which is based on feature maps extracted from a pre-trained VGG network. Together, these losses help SRGAN focus on both realism and perceptual quality, going beyond traditional pixel-based metrics. The generator architecture employs residual blocks to preserve high-frequency details, followed by the pixel shuffler layers for efficient upsampling. This design enables the network to maintain important textual information throughout the reconstruction process. And the key innovation lies in the perceptual loss function. SRGAN combines three loss components: adversarial loss from the discriminator, perceptual loss from VGG feature maps, and traditional MSE loss. The VGG perceptual loss extracts features from a specific intermediate layer of a pre-trained VGG network, measuring L2 distance between feature representations rather than raw pixels. For our project, we've implemented and trained both SRCNN and SRGAN models. Here, you can see one example using an image of a car. We ran both SRCNN and SRGAN to see how each model reconstructs the high-resolution version. When comparing SRCNN and SRGAN outputs, the differences are immediately apparent. SRCNN produces smooth, artifact-free results that score well on traditional metrics like PSNR. However, these images often lack the fine details and realistic textures that make images visually compelling. SRGAN, in contrast, generates sharper images with more realistic textures. While this sometimes introduces slight artifacts or color shifts due to batch normalization, the overall perceptual quality is significantly improved. This leads us to a fundamental question. How do we properly evaluate super resolution quality? Traditional metrics like PSNR and SSIM fail to capture what makes an image look realistic to human observers. Then, what is PSNR and SSIM? PSNR measures pixel-wise differences in decibel scale, while SSIM evaluates structural similarity considering luminance, contrast, and structure. Both metrics provide objective measurements, but they don't align well with human visual perception. As the SRGAN authors noted, standard quantitative measures such as PSNR and SSIM fail to capture and accurately assess image quality with respect to human visual system. This limitation became apparent when mean opinion score testing showed that humans preferred SRGAN results despite lower PSNR scores. This disconnection between objective metrics and subjective quality highlighted the need for better evaluation methods that consider perceptual similarity rather than mathematical differences. Then a modern perceptual evaluation emerged, the LPIPS. LPIPS, introduced in 2018, addresses these limitations by leveraging deep feature representations for perceptual similarity measurement. The approach computes feature maps from pre-trained networks like AlexNet or VGG, then measures distances between these representations. The training methodology uses two AFC paradigms where human observers choose between image pairs. This creates a dataset of perceptual preferences that can train the metric to align with human judgment. We've implemented LPIPS using the AlexNet-Lin variant, which is a learned perceptual similarity metric. The Lin in LPIPS AlexNet-Lin refers to a version where the feature embeddings from AlexNet are passed through a small linear layer that is trained to better match human perceptual judgments. Instead of relying only on raw distances in feature space, this version learns how to weight different features based on human-rated image similarity. We've trained this linear layer using the BEPS dataset, which contains pairs of images along with human preferences for which one looks closer to the reference. This allows LPIPS to better align with what people actually perceive as visually similar. However, our validation accuracy was approximately 3% lower than the published benchmarks. The slight performance gap in our implementation likely stems from differences in image preprocessing and cropping methods. Our evaluation results demonstrate clear performance differences between two approaches. Using both our implementation and the official LPIPS package, SRGAN consistently outperformed SLCNN in perceptual similarity metrics. These results validate the effectiveness of adversarial training and perceptual loss functions for super resolution. In summary, we've traced the evolution of super resolution from SRCNN's pioneering CNN approach to SRGAN's perceptual optimization strategy. SRCNN established the foundation for deep learning-based super resolution with its simple yet effective architecture. SRGAN advanced the field by introducing adversarial training and perceptual loss functions, achieving more realistic results despite potentially lower traditional metric scores. LPIPS represents the modern approach to perceptual evaluation, providing metrics that better align with human visual perception. This progression highlights an important trade-off in computer vision, optimizing for mathematical metrics versus visual quality. The key lesson is that the choice of evaluation metric significantly influences algorithm development. The key lesson is the choice of evaluation metric significantly influences the algorithm development. As we move forward, perceptual metrics like LPIPs will likely play increasingly important roles in guiding super resolution research toward human-centric objectives. And thank you for your attention. Any questions?